In the first lecture here for 19, mainly concepts. There's a couple problems at the very end, and the thing I want to focus in on chapter 19 is really, at least early on, getting the point across of what is a spontaneous reaction and how do we know when we have one. When you listen to the series of lectures for chapter 19, they're not going to correspond directly with the outline in the chapter in the textbook. I'll just tell you that right now. So I'm jumping around a little bit, but I find it to be very important to establish early on this notion of a spontaneous reaction, and then get into this concept of a irreversible reaction. There's a corresponding reversible reaction, which honestly I'm not going to deal with a lot with. I'll touch on it here and there. But I mainly just want to get through, the essential portions of this chapter, so that you get a good appreciation for this particular aspect of thermodynamics, without getting too bogged down in the sort of abstract mathematical concepts. Okay, so first off, this concept of a spontaneous reaction, and you can see the definitions here. The main thing is that once you get it started, once it's initiated, the reaction, it goes without the input of energy. And so you'll see one example. I'll just go ahead and fast forward. This hydrogen filled with or this balloon filled with hydrogen. You set the light to it and it automatically explodes. That's a spontaneous reaction. So once you get it going, it goes by itself. It doesn't require constant input of energy. Traveling down the road in your vehicle is not necessarily a spontaneous reaction. You have to constantly put energy into that vehicle to keep it going. So just give you a comparison there of what we mean by spontaneous reaction. And there we have a non-spontaneous process. You constantly have to put energy into the system. Now, for example, another type of spontaneous reaction would be this system that we have here. This is pulled from the book. You have two flasks connected by a stopcock. Right now, it's a closed stopcock, and then the yellow over here indicates gas particles floating around. And then as you open the valve up, what is it going to do? Well, the gas has a natural tendency to go from a high concentration area to one of low concentration. In this case, it's completely evacuated, and so you'd say this is under vacuum. So it's a very spontaneous process. Once that stopcock is open, the gas molecules are not going to stay isolated in that one spot. Both of these examples that I've talked about, they're sort of intuitive. Once you start thinking about it, you can see that they're spontaneous. Well, that's not good enough for us. We want to actually be able to quantitate, and this is jumping down to this last topic here, the last bullet. How do we determine a spontaneous reaction? It's not just by investigation. It's actually going through a mathematical process and generating some concepts along the way that's going to be very helpful for us. Okay. Now, before we get into the guts of this notion of how we determine spontaneity in a reaction, let me just say a word about the different types of reactions that you're going to read about in the text. You're going to read about reversible reactions and irreversible reactions. Well, the first thing I want to get across, I'm actually going to mark out practically. An irreversible reaction, well, all the chemical reactions we're describing are going to be irreversible. So the definition of a reversible reaction is, and I guess we can use the two flask system here. If this is a reversible reaction, then you would somehow be able to backtrack from this point to that point following the same pathway. And that's impossible. There's no way that these molecules in A are going to jump over to the flask B. Okay, that is one aspect of a reversible reaction. There's an additional perspective of it in terms of a slow, instantaneous, or infinitesimal change in the reaction from point A to point B, and then from point B to point A back to, or from point B back to point A. Okay, and again, I don't want to get too bogged down into some of these abstract concepts that physical chemists love, because you guys most likely are not going to be physical chemists, or maybe even chemistry majors. So I want to give you a sort of a good appreciation for this notion of spontaneity, and then as we mature in our understanding of this concept, then I may come back and touch a little bit more on some of the more abstract concepts. Okay, and so just know that the reactions we're going to see, all of the reactions we've seen in our chemistry career, are irreversible reactions. Again, to be reversible, you have to follow that exact same path to the original point, and that's just not what happens in nature. A reversible reaction doesn't violate the first law of thermodynamics, that law of conservation of matter. It's just that it's just not going to happen. We know that doesn't happen. There's no way that the heat and the water vapor that's produced in this reaction is going to be able to come together to form the balloon of hydrogen gas that we have here. That's just not what's going to happen. We wouldn't violate anything about the first law of thermodynamics, meaning the mass and energy here equals the mass and energy here. Conservation of mass for the first law. That's not violated. We just know that this particular process just doesn't occur. Okay, that would be a reversible reaction. So what are we looking at here? Well, we're looking at a spontaneous reaction, and it's irreversible. Once the water vapor is formed here and the heat's released, it dissipates. Okay, that's the basic observation that one would see in this kind of reaction, along with a fairly large boom. Okay, so our job here, getting back to spontaneity, what criteria do we have to factor in whether we can predict something is spontaneous or not? Now, this is an exothermic reaction, meaning, well, here we go, negative enthalpy. This would be, this is actually going back to Chapter 5 in Brown and LeMay. Gen Chem 1 is where we first saw this concept of enthalpy. And just briefly, just think of it as heat. Okay, it's a little bit more subtle than that. It's a little bit more complicated, but it's essentially just heat. We can see this is a good example to start off this discussion, because we know this is an exothermic reaction. We're going to feel the heat coming off of it in the process. Now, early on in the study of thermodynamics, scientists believed that, well, if something is exothermic, that must be the measure of whether the thing is spontaneous or not. Well, what you may want to ask yourself are there any endothermic spontaneous reaction? And there is one good example. There's more than just one, of course, but this is a good example, I think, a solution formation of spontaneous. If you take a beaker full of water and you put a little bit of sodium chloride in it, what are we describing here? We're describing something very simple. The formation of salt water. This happens very easily. Any salt that's soluble in water goes in that solution very easily. We can see the schematic diagram here. Look what's happening. We have this block of sodium chloride here, and these individual water molecules that are fairly randomly organized outside of the salt crystal, and as it comes in, there's a particular association that's occurring between the ions in the salt crystal and the water molecule. For example, we'll just look at, let me do a couple of Lewis structures here for this guy. The purple sphere is the sodium cation, and so it would be placed in the center here. And then the water molecules, what you can see are the red spheres associating themselves with the Just draw a couple. The red spheres are the oxygen atoms, and there's a delta positive there. So there's a favorable interaction that's occurring between the solute and the solvent molecules to disperse the block of solid that you have in there, and you see eventually all of the solute molecules gets distributed out through the solution. This is a spontaneous process. Well, and it's definitely an endothermic process. If I place a thermometer in your average salt being dissolved in a solution, you're going to see a decrease in the temperature. That's an indication of an endothermic reaction. So endothermic reaction, let me get some of the notations up here that I have included. This is a positive value, and heat is absorbed by the reaction. Now, this concept was first introduced in Gen Chem 1, Chapter 5, but that's just a reminder of the sort of the end result of everything, the conclusions that were reached with this notion of endothermic versus exothermic reaction. And we know this is spontaneous. So this, that early simple notion that an exothermic reaction was spontaneous, that did not factor in all possibilities. And that's one thing that drives scientists crazy. We want a model, a theory that can factor in, every single example that we're coming across out there in nature. And so what's happening is that we're developing a more complicated theory than just saying exothermic reactions are spontaneous. That's a simple statement, and it's simply not true because there's endothermic reactions. So what we do is we introduce a new term, and we bring that into a new formula as well. Okay, and we'll see that in a couple of slides. So this notion of entropy is introduced for this particular concept to explain why this solution formation is spontaneous, and there are a variety of definitions of entropy and the second law of thermodynamics, which gets introduced into this in this particular chapter, especially the second law of thermodynamics. There's a lot of variations in the statement of that law, depending on what perspective you're coming from. And for entropy, just simply think of entropy as a measure of randomness, and what we're going to find out is high entropy randomness is actually favored in nature. It's the kind of thing that it's one of the driving forces for this solution formation. All the ions that are trapped in this particular solid salt here have a very low degree of randomness, a very low entropy, and so we'll just go ahead and label that. We'll say low entropy. We'll use our symbol S for it, and then by the time it gets completely dispersed, now the solute molecules, there's actually been an increase in entropy for the solute. And that is the driving force behind this particular reaction. And again, in a couple of slides, we'll put it together so we can see the exact, the important concept that we're developing here. We have to combine enthalpy and entropy into a single equation to predict spontaneity. That's where we're headed. Okay, but first I want to talk about why is this notion of randomness, why is that favored in nature? And the example that I'm going to use this example. It's from the book. It's a different hands of poker, and what does it mean in terms of a statistical analysis, if you will, and how does that relate back to this notion of entropy? Well, if you're familiar with the game of poker, you're a avid follower of the poker World Series or whatever they call it on television these days, you should recognize these two particular hands that are listed on the slide here. The first one here is a royal flush. It's the highest hand that one can attain from in a poker game. And what you see is ace, king, queen, jack, and 10 of the same suit of cards. This is a very, there's 51, 52 cards in a deck. In a game of poker, to be dealt these 5 cards specifically from a randomly shuffled pile of 51 or 52 cards is highly unlikely. There's only 4 possibilities for this particular hand. The 4 coming from the 4 suits: spades, hearts, diamonds, and the clubs, clover-looking thing. And it's highly unlikely, highly unfavored that you're actually going to get a royal flush in poker. Whereas the chance of getting nothing, what's the chances of being dealt 5 random cards that match with no special hand in poker? Well, it's well over a million times the number of hands that you could actually, the number of combinations where you actually get nothing is much higher than the number of combinations where you get a royal flush. And so in terms of a favored microstate, if you will, this would be, I don't want to introduce too many terms here, but this term microstate, actually what do the individual cards or what do the individual molecules actually look like? What are their particular individual properties? This microstate, well, there's 1.3 million chances of getting a random nothing state versus 4 for a royal flush. And so this notion of probability plays a major role when you start digging a little deeper into entropy. Why is randomness favored? Well, it's just more likely to occur than something that's in a very organized system like we have for the royal flush. It's just less likely to get a nicely organized, compact state, whether it's in poker or whether it's in a chemical reaction. And so the chances of acquiring something is playing a role, and the chances increase as you get into a more random system. There's many more microstates available for this look that we have on that third picture, then the chance of all of these molecules just coalescing as a simple little a block of sodium in the middle of the solution. And so this notion of probability, or what's called statistical mechanics, plays a large role in terms of a deeper understanding of entropy. And I don't want to go there. That's beyond the scope of the course. There's many things in this particular topic that we're starting in Chapter 19 that is beyond the scope of the course, and this is one of them. I just want to give you just a little bit of an understanding of some of the terms you're going to see as you go and read this this chapter. Okay. So just remember, more random, more highly favored. That's essentially the take-home message from this particular slide. Now let's put these two concepts, meaning enthalpy and entropy, together. Now, the book goes through a rather lengthy discussion of this particular equation, and we may have time for that in class. You may see it in parts of the next couple of lectures. But really what I just want to do is sort of just give it to you, and not get bogged down in some of the subtle details of some of this topic, because what you start doing, I think, a student, when they first get a hold of this material, can sort of lose sight in terms of what they're after. And remember, what we're after is an understanding of spontaneity in a chemical reaction. Okay? So what we have here is this delta G is referred to as Gibbs free energy. And again, it is the term that one uses to decide whether something is spontaneous or not spontaneous. And I'm just going to go ahead and give you the the take-home message, if you will. If delta G is negative, then you have a spontaneous reaction. If delta G is positive, then you have a non-spontaneous reaction. That's essentially as simple as it gets. And again, for the moment, I'm just ignoring the derivation of Gibbs free energy. Okay, I want to be able to use the thing. It's more important than actually. I want you to understand where it's coming from a little bit. Okay, but that sort of need to be face to face for that, honestly. So that I'll tackle that in class. And again, you may see it on here and there for the later part of the presentations for this chapter. And notice what the Gibbs free energy is made up of. Well, there's three variables. We have the enthalpy here, we have entropy here, and then T, of course, is temperature. And essentially it's a play between, what is the contribution in terms of the heat, is it exothermic or endothermic, and then what is the contribution of the randomness of the system. Because remember, and I'm going to go back to a couple of slides. Remember early on is the exothermic reaction, is that the criteria that we use to determine spontaneity? Well, not quite. It works in some cases, but not in all. There's an endothermic reaction that still happens to be spontaneous, and here we have this increase in randomness of the system. And so what Gibbs free energy does is it brings these two concepts together in, honestly, a very simple, compact equation so that then we can determine spontaneity based on the value of Gibbs free energy that we calculate. And so, again, spontaneity depends on heat content, on the randomness of the system, as well as the temperature at which the reaction is occurring. For example, the melting of an ice cube is spontaneous above 0 degrees Celsius. It's non-spontaneous below 0 degrees Celsius. So there is a temperature dependence on a spontaneous process, and we'll see that in some examples as we go through the next few lectures in class, and also you'll see the examples in the book as you read that chapter. So let's look at, we both know that both of these processes are spontaneous. Let's just get an amen from the Gibbs free energy and see how it's factored into this part of the discussion. Now, I'm not going to put a lot of numbers with this. This is still essentially a qualitative game, a game that we're playing here. Again, the Gibbs free energy component, what is it made up of? It's made up of the enthalpy portion, and then it's made up of the negative delta T, negative T delta S portion. Again, heat and randomness is what we're measuring here. So in this particular process up here, now we know it's the enthalpy change is negative. It releases heat during the process. It's exothermic. And so we can say that this process is negative, or this portion of the Gibbs free equation is negative. That is promoting, remember, we have to have delta G being negative if we have a spontaneous reaction. These 2 points are very important to remember throughout the entire chapter. Once you watch this first video, you may want to go back and reread the first few sections here, and because you sort of know where you're heading. This is sort of what I'm telling you. This is our one of the important goals or capstones of the chapter, is to establish this equation. And what I've done is I've just given it to you. I've just said, well, here's the important point, and so now you can, as you reread those first few sections in the chapter, with this particular knowledge, the very, very clear conclusions here might help you put together some of the abstract things that you're reading about in there. Okay, so again, you're factoring in two measures here. Now, I will tell you, in this particular experiment, I actually had to calculate delta S. I couldn't just easily, I'm getting a little bit ahead of myself, but the reaction that's going on here, oops, that should the parentheses is here. Let me just do that. Oxygen, gas, yield is still pretty hot, so it's 2 moles of water vapor. Now in the second lecture, you're going to see a more detailed analysis of what entropy means and how you judge entropy. Well, one thing you can judge is the number of gas molecules, or number of moles of gas. Let's just say gas molecules. You have 3 gas molecules here, and you only have 2 gas molecules on the product side. And so you actually get a reduction in entropy. The more gas you have, the more entropic the system is, the more random the system is. And so when I'm looking at this particular equation, I said, well, that's certainly clear that this is a higher degree of entropy just based on the phase that you have in front of you. And then over here, the measure of entropy is also a function of how complicated the molecule is. I mean, the water molecule isn't terribly complicated, but it does have more, let's say, molecular microstates. It has more molecular motions than either the oxygen or the hydrogen molecule, diatomic molecule here. And so the molecule itself has a little bit more randomness, a little bit more of an entropic factor, if you will. Anyway, long story short, actually I calculated the entropy change here, which you'll see for the second video, how you do that. And I got a value of, just for delta S, I got a value of negative 88 joules per mole per Kelvin. The units will be more fully explained in the second video, so don't worry. I just want to get this equation out there and how we use it for spontaneity. So notice something about this particular expression. There is a negative term here that you must factor in. If you don't factor in the negative term, you are going to have trouble. Okay? So you got a negative times a negative. And so what we actually see is this portion of the expression is actually positive, but only slightly. In the grand scheme of things, it's only a slight increase in this portion of the equation. And so what you see is a negative being combined with a positive value. Well, this is large. If anyone has ever done this demonstration for you, there's a lot of heat that's kicked off in this particular reaction. And so the negative value of the enthalpy component overrides the slight positive value of this overall expression in the second half of the equation. And so that the net result is Gibbs free energy for this particular process is a negative value. And if we could go through and calculate this from tabulated values, and we would see that it's true, and we'll do one of those calculations here in a minute. Whereas on the other side, again, I'm going to do the same thing. What are the components? I'm not talking about, just entropy and then just enthalpy. I'm talking about there's one component dealing with the heat and there's one component dealing with the randomness. And I've included that negative sign on that randomness side of the table here. And then, my question is, well, what's delta G? Well, I mean, I've already told you this is a spontaneous reaction. We know salt dissolves in water, so we know this is going to be a negative value. So I guess negative is already known. But let's put it together here. So this is an endothermic reaction. So remember what that means. The endothermic reaction is a positive delta H, but only slightly. It only absorbs a little bit of heat, essentially, is what I'm trying to say. Whereas the entropy factor here, we're going from, let me back up, I'm losing some room here, so let me, that slide. Remember, that's the description of the chemical reaction that's occurring. I mean, there's some issue with the solvent cages, but that's beyond the scope of the course, okay? Look what's happening in this particular equation. You have a solid block with a very low amount, again, phase matters. This solid, and we'll see this in the second video, solid phase has a very low entropy, very low randomness. You know, there's some small vibrations within the salt, but there's really no, you wouldn't talk about kinetic energy or kinetic motion for this particular system. It's just locked into a solid. Whereas these solute molecules are freely floating, and again, the number of microstates, if you will, the number of possible arrangements of all of these millions and billions of ions is enormous. And so there's a high degree of randomness when it goes from this transition from an aqueous, or from a solid to an aqueous system. And so as a result, you know, we have delta T, whatever temperature, we haven't even really dealt with that, room temperature. And then remember, this thing is extremely positive. And so when you multiply these two together, this positive value times room temperature, and then you factor in the negative here, this is very negative. And again, it's due to that randomness, those huge number of microstates. That how many different ways can you arrange these millions and billions of solute ions in solution? Well, again, it's an enormous value. And so this high degree of entropy, this positive entropy, makes this a very negative contribution to Gibbs 3. And that's what drives this finally to the negative side of the when you're calculating the delta G here. And again, what we're doing here is more of a qualitative measure. We haven't really put many numbers to it. I had to do it here because, you know, I couldn't just look at the equation and tell you exactly what was going on in terms of entropy. The next one I can. We have a combustion reaction, and I'll just go ahead and say, you know, if you have a combustion reaction, that means the delta H is less than 0. It's a negative value. Remember, negative delta H is exothermic, is going to push delta G down. So we have a contribution of a negative from the delta H. And look what the question is asking. It's sort of strangely worded to some degree. Would you expect delta G to be more negative or less negative than delta H? Okay, so we already know delta H is negative. How much more negative, or is it more negative? Is delta G more negative or less negative than this value that we already sort of intuitively know? How do we figure out something like this? Well, what do you know? You know, let's look at that simple equation that I gave you earlier. We already know this is negative. And this is a combustion reaction. Any combustion reaction of a hydrocarbon is a spontaneous process. And so we already know this is negative. We just don't know how negative it is. Okay? We want to know whether it's more or less negative than this delta H term. So what it requires us to do is to analyze that part of the Gibbs 3 equation. Minus T times delta S. In this example, again, we'll look at this more closely in the second video. Phase matters. Phase is one of the most important aspects of whether entropy is increasing or decreasing. You know, again, think about solid to aqueous phase, or aqueous solution. That's a huge jump in entropy. There's a high degree of randomness in all these ions floating around an aqueous solution, whereas if it's a solid, there's a very low degree of entropy. And we'll, again, second video, we'll see that. The phases here are all the same. That's actually helpful for us. What we go in, we go in here, and what we do is we add up the number of gas molecules on each side. We have 6 gas molecules here. And it doesn't matter how complicated the thing. Again, phase is a really strong driving component in terms of entropy. Okay, there's 3, 4, there's 7 gas molecules here. This is more entropic. Therefore, delta S is positive, and that's a good thing. If we then, again, this is not quantitative. This is qualitative. This is estimating delta G. You know, if we think, okay, well, delta S is a positive value, you have a positive value here being multiplied by a negative value, well, you have a negative plus a negative. And so as a result, this is even more negative than what we started out with the enthalpy change. So the answer to this particular problem is that delta G is more negative than delta H because of the high degree of entropy in this particular example. And the entropy is just is simply estimated based on the number of gas molecules that increases or decreases. You know, if you have like going in the other direction, a decrease in the number of gas molecules would be a reduction in the entropy. Entropy would be negative at that point. Now the last problem that I want to do is actually a quantitative problem, and it's dealing with how do you calculate delta G. There's a variety of ways. We'll see all of them, but this equation by far is one of the most useful ones. And I'll just go ahead and tell you, there is a corresponding equation for both enthalpy and entropy that looks very similar to this. There's for the enthalpy one, for the delta H naught of reaction, you got to go back to chapter 5 to see it. And then the entropy one is in this chapter, but they all take on the same form. Essentially, you calculate the contribution of Gibbs free energy of the products, and then you subtract the contribution of the Gibbs free energy of the reactants. Products minus reactants, final minus initial. That's a very common theme that one sees in science. You know, if I want to talk about delta T, which actually I don't know if you'll see that, but you've seen it before in first Gen Chem, delta T, anytime you have a delta, it's always final minus initial. And so this theme of final minus initial runs throughout chemistry, just in one form or another. The sigma here means summation. So what you're doing is you're adding up the Gibbs free contribution of the product side, and then you're subtracting the summation of the Gibbs free energy from the reactant side. There's a couple aspects that we have to worry about here. One is, what is Appendix C? You should look at Appendix C. Okay, actually I have an example of it on the next slide. Appendix C is a big table, and what it does is it lists different substances, and it shows you the enthalpy formation, Gibbs free formation, and then the entropy for those different chemicals or elements. And it's from this table that you find your values. There's your delta G of formation. So what it's measuring is, well, how much? Actually, let me get a new slide for this one. A formation reaction. Well, let's say for the formation of water, you know, what are its chemical components? You have oxygen and hydrogen. So the formation of one water molecule is dependent upon, you know, oops, actually that's not 1/2. This is 1/2. This goes back to chapter 5 from Gen Chem 1, by the way. So all the values you see for water in the gas form is dependent upon this particular equation. You know, you're talking about the and again those three: the enthalpy of formation, the Gibbs free energy formation, and then the entropy of formation. And I'll have more to say about the differences here on the last slide. But simply put, it's you know, how much heat is released or absorbed for this particular equation, and then what is the Gibbs free change for this particular equation. And it's the same kind of song and dance. If this is a negative value, then one would say, well, this is actually a favored process. If this is a negative value, then we'd say it's exothermic, which is the case. And you can see and you know, I'm just giving labels here, a qualitative description. The tables gives you a quantitative measure, and we'll see this one coming up in the calculations here. So, the conclusions that we've reached up to this point are still valid. We're just applying it to a very specific type of equation. And what it allows us to do is to take that tabulated data for the formation of these different elements and compounds and be able to predict the Gibbs-free change for an overall reaction. And so when we look at, let me change this, the N and the M represents a number of moles. It depends on how much of the matter is actually there. So the number of moles, 1 to 2 to 3, is going to affect, well, either whatever you're calculating, whether it's delta G, delta H, or S. Okay, so keep that in mind. And then again, these things are just from Appendix C. And you will want to look at that part of the book. That'll be given to you on the test. I don't ever expect you to memorize such a large table. That's madness. Let's put this equation to practice here and calculate the delta G for this particular reaction. We already know it's spontaneous. Hydrocarbon burning is spontaneous. Once you spark it, it goes, as long as it has plenty of oxygen around. So it is a spontaneous reaction, so we should expect a negative delta G. Let me put it all together. And again, we're looking at the overall reaction here. Summation of the products. I have 1 mole of carbon dioxide and I have 2 moles of water. And so if I look at there's our carbon dioxide part. And if I look in the table, 394.4 kilojoules per mole. So that's a Gibbs-free change for the formation of 1 mole of the compound of carbon dioxide. Summation tells me that I have to add the contribution of carbon dioxide and then also the 2 moles of water. If I look at the table, then the heat of formation, or the Gibbs-free energy of formation, I should say, is negative 228 kilojoules per mole. And that's I only have 2 products, so that's the end of that particular summation portion. So that's the end of that portion there. And then the second half, this guy is negative. And I have 1 mole of methane. And it comes in at only minus 50.8 kilojoules per mole. Remember, products minus reactants. And then it turns out, yeah, I got 2 moles of oxygen. But and I'll talk about this in the next slide, delta G and delta H of formation, 0 for elemental forms. I guess that's the only one you have to memorize, because I may give you an abbreviated Appendix C for you. So if you see diatomic oxygen, diatomic hydrogen, any of the elements, aluminum, gold, carbon, all of them are 0 in their elemental form, in their simplest form, and I'll explain why in the next slide. If you look on the table for oxygen gas, you will literally find it listed at 0 kilojoules per mole. And so essentially, I mean, this drops to 0. In any elemental form, in either one of these calculations turn out to be 0. They're not factored. Well, they're factored in, but they're 0. That's not the case for delta S. Delta S is a completely different story. Okay, so the elemental form for delta S is non-zero. You can little preview. There's aluminum. You see, it's 0 here, 0 there. For the S naught is 28.32. So it's not 0, and that's typical. Okay. If I go through this calculation, what I get is a negative 800.74 kilojoules, which is what I expected. It's a spontaneous reaction. I knew that. It's a combustion reaction of a hydrocarbon. That's just how it is. Negative 800 kilojoule per reaction as written, meaning the combination of 1 mole of methane and 2 moles of oxygen to form this, is negative 800.74. If I doubled everything, then I would double this amount. It's a extensive property. It depends on how much you actually start with. Hindenburg blowing up back in the 20s gave off a lot more heat than this little balloon filled with hydrogen. Okay, so thermodynamic properties oftentimes are extensive. It depends on how much you actually have. Last slide, this last concept, and it feeds back into what I was just talking about. Delta G, delta H are relative values. It's sort of like an altitude. If you have, so we have Asheville up here, and this is the beach. And this is Asheville. The change here is about 2,100 feet or so, depending on what part of Asheville you're standing at. This is a relative value. This is an absolute. We humans have established 0 feet at the beach, and then everything is scaled up and down with respect to the beach, to this 0. Humans could have just as easily said, okay, we're going to make this 50 feet, and then scale everything from that point. That'd be a little silly to do, but they could have. This 0 value for feet is arbitrary at the beach. And so this is altitude as a relative scale. Well, as it turns out, and I'll explain this a little bit more in detail in the second presentation, but just know that delta H and delta G, both of these, they're relative scale like altitude here, and we had to establish a sea level, if you will. 0 feet at the beach, that's our reference point for altitude. That's our reference point. Humans have decided that's a convenient way to mark the 0 point. Well, chemists have concluded that the 0 point, the reference point for chemical reactions, is the elemental form. So the elemental form is the reference point for chemical reactions. And then, as aluminum is converted into other compounds, such as aluminum chloride or aluminum oxide, then, you have a change in the delta H and the delta G with respect to that 0 point of the elemental form. Now notice, and this will lead into the second presentation, delta, or S naught, standard, the naught means standard conditions, that is not relative to the elemental point. The reference point is not the elemental point. Actually, the reference point here is 0 entropy at 0 Kelvin. So, reference point for entropy, delta S is 0 at 0 Kelvin. And again, that's leading in absolute temperature scale. That's leading into the second presentation. S is not relative. There is a bottom. There is some point in nature where delta S becomes 0, and it just is. Humans didn't decide that. It just is. There's 0 entropy at 0 Kelvin for any substance. That's not the case. Again, that's not the case for delta H or delta F. It's all a relative scale, no matter what compound you're looking at, no matter what temperature. And we had to choose some kind of arbitrary point to begin our discussion, to begin our 0, our reference point. And chemists chose elemental form. Whereas, elemental form at room temperature is going to have some kind of entropy to it. It's going to have some kind of randomness. It's going to have some kind of molecular motion, some kind of system of microstates, if you will. Okay, and that is what we're going to start off with in the second lecture for this chapter. Okay, thanks.